Imagine you're trying to blend oil and water in a miniature, precision-engineered kitchen where these two liquids, which naturally repel one another, are forced into a delicate state of coexistence. In this microcosm, tiny droplets of one liquid are suspended within the other, forming an emulsion that is as much an art as it is a science. Picture a chef using modern culinary techniques to create a complex sauce. Each ingredient must be measured and combined with exact precision so that the final product is both harmonious and stable. In microfluidic devices, where channels are measured in mere micrometers, the control over these droplets is paramount. Even the smallest imbalance can lead to instability and separation. For example, in a lab-on-a-chip device used for biochemical assays, maintaining the precise size and composition of each droplet can be the difference between a successful diagnostic test and a failed experiment. One might ask, what happens if these droplets become unstable? The answer is that instability can lead to coalescence, where droplets merge together and lose their discrete identity, undermining the precision required for processes such as targeted drug delivery or high-throughput screening. At the core of this sophisticated process is interfacial tension, an invisible force acting along the boundary where two immiscible liquids meet. Imagine a perfectly stretched elastic membrane that encloses a group of small objects. This membrane pulls tightly, minimizing its area, much like how droplets form nearly perfect spheres in nature. This phenomenon can be compared to a soap bubble, where surface tension keeps the bubble intact and uniformly round until disturbed. In microfluidic applications, lowering interfacial tension is often achieved by adding substances that act as lubricants at the molecular level, allowing droplets to form more easily and remain uniform in size. For instance, when manufacturing emulsified drugs, reducing interfacial tension is critical to ensure that the active pharmaceutical ingredient is evenly distributed throughout the formulation, ultimately leading to improved efficacy and patient outcome. One might wonder, what happens if the interfacial tension is too high? The answer is that excessive tension makes it difficult to create small droplets. They may form irregularly or merge uncontrollably, resulting in a system that is unpredictable and difficult to control. When streams of immiscible fluids converge within a microfluidic channel, the process of droplet formation begins in earnest, much like traffic merging at a busy intersection. In these tiny channels, the delicate balance between fluid velocities, viscosities, and the specific design of the junction determines the size, frequency, and uniformity of the droplets that are produced. Imagine two high-speed highways coming together. If the timing and speed aren't perfectly coordinated, collisions or erratic behavior might ensue, similar to droplets coalescing or breaking apart prematurely. For example, in digital PCR applications, the precise formation of thousands of uniform droplets is essential for accurate DNA amplification and quantification. When asked how a slight change in one fluid's velocity might affect the overall outcome, the answer is that even a small imbalance can lead to droplets that are either too large, resulting in reduced reaction efficiency, or too small, which might fragment and cause loss of material, ultimately affecting the precision of the analysis. The physical design of microchannels is as critical as the chemistry of the fluids they carry, directly influencing the behavior and stability of the droplets. Think of these channels as racetracks on which droplets travel. A well-designed, smooth track enables the droplets to move steadily and predictably, while a rough or poorly designed pathway might lead to disruptions that cause droplets to merge or break apart. For instance, in a microfluidic device used for synthesizing nanoparticles, uniform channel geometry ensures that each droplet experiences consistent shear forces, resulting in uniform particle sizes, a key factor in the performance of catalysts or drug delivery systems. One might ask, have you ever observed how water droplets bead on a freshly waxed car? This observation demonstrates that surface properties can dramatically influence fluid behavior, and the answer is that by controlling these surface properties, whether through hydrophobic or hydrophilic treatments, engineers can direct droplets to behave in a predictable manner, ensuring that the system remains stable and effective. Surfactants, the molecular agents that dramatically influence emulsion stability, act like skilled mediators between two inherently incompatible liquids. These molecules have a dual affinity. One end is attracted to water and the other to oil, enabling them to position themselves at the interface and reduce the natural interfacial tension. This reduction is akin to lowering the tension between two feuding parties, allowing them to coexist peacefully. In practical terms, when a surfactant is added to a system, it forms a protective layer around each droplet, preventing them from merging uncontrollably. Consider the example of mayonnaise in culinary arts, where egg yolk acts as a natural surfactant to combine oil and vinegar into a stable emulsion. In microfluidic devices, similar principles are applied, and the careful selection of a surfactant, taking into account factors such as critical micelle concentration and biocompatibility, is essential for applications like drug delivery, where the stability of each droplet can affect the controlled release of medication. When asked what potential issues might arise if an inappropriate surfactant is used, the answer is that a mismatched surfactant can lead to toxic byproducts, inadequate reduction of interfacial tension, and ultimately droplet instability that compromises the entire process. Engineering the microfluidic channels themselves is an intricate process that blends advanced fabrication techniques with a deep understanding of fluid dynamics and material science. Using cutting-edge methods such as 3D printing, engineers can create channels with complex geometries tailored to optimize droplet formation and movement. Imagine designing a custom-built racetrack where every curve, straightaway, and pit stop is meticulously planned to maximize performance. This is exactly what happens at the microscale in these devices. For example, researchers have developed channels with gradual curves and smooth transitions that minimize turbulence, ensuring that droplets are not subjected to disruptive forces that could cause them to coalesce or break apart. One might ask, how could the introduction of a novel material, such as a graphene-based coating, revolutionize droplet formation and stability? The answer is that such advanced materials can dramatically enhance the channel's properties by improving its thermal conductivity, chemical resistance, and surface uniformity, thereby facilitating even more precise control over droplet behavior, though they also pose challenges in terms of integration and cost. The most effective microfluidic systems harmonize both chemical and physical strategies to achieve droplet stability that is greater than the sum of its parts. This integrated approach is comparable to tuning both the engine and suspension of a high-performance car to ensure a smooth ride. Every component, from surfactant formulation to channel design, must work in concert. In practice, researchers often experiment with combinations of surfactants and additives to rapidly adsorb at the droplet interface, creating a robust protective barrier that prevents coalescence even under dynamic conditions. An illustrative example can be found in bioanalytical chemistry, where a blend of non-ionic and ionic surfactants has been used to stabilize droplets carrying delicate biological samples, ensuring that each reaction occurs in a controlled environment. When asked how one might design an experiment to test the interplay between chemical additives and channel design, the answer is to systematically vary one parameter at a time, such as altering surfactant concentration while keeping flow conditions constant, and then measure droplet size and stability using high-speed imaging and statistical analysis, thereby identifying the optimal combination for the desired application. Real-world applications of microfluidic emulsion technology are both diverse and transformative, impacting fields as varied as biomedical diagnostics, chemical synthesis, environmental remediation, and food production. In the realm of medical diagnostics, for example, stable droplets are used in techniques like digital PCR to isolate and amplify DNA, ensuring that each droplet functions as an independent microreactor with uniform conditions. This precision is critical for accurately detecting low-abundance genetic markers in complex samples. In another scenario, microfluidic devices are employed in the synthesis of nanoparticles, where uniform droplet size translates to consistent particle sizes, a factor that is crucial for applications in drug delivery and catalysis. For instance, a company developing targeted cancer therapies might use microfluidic emulsions to produce nanoparticles that deliver chemotherapy drugs directly to tumor cells, thus reducing side effects. When asked what innovative applications might arise from such technology, the answer is that advancements in microfluidic emulsions could lead to personalized medicine, on-demand drug synthesis, and even new methods for environmental cleanup by encapsulating and releasing remediation agents in a controlled manner. Despite the remarkable advancements achieved in microfluidic technology, significant challenges remain when attempting to scale these systems from the controlled environment of a research laboratory to the unpredictable conditions of industrial production. In a lab, researchers can fine-tune every parameter to achieve precise control over droplet formation, but scaling up introduces variables such as increased flow complexity, environmental fluctuations, and the need for real-time monitoring and adjustment. For example, in a pilot-scale production of emulsified cosmetics, maintaining uniform droplet size and stability across a larger device is much more difficult due to variations in temperature, pressure, and flow rates. When asked what the most pressing obstacles are to scaling up these technologies, the answer is that challenges include maintaining consistency, ensuring robust automation, and integrating advanced sensor networks to dynamically adjust operating conditions. Emerging innovations in automation, artificial intelligence, and materials science are poised to help overcome these hurdles by enabling more resilient and adaptive systems. Ultimately, the study of emulsion stability in microfluidic devices is a fascinating journey that lies at the intersection of chemistry, physics, and engineering, a realm where minute droplets serve as both subjects and vehicles for scientific innovation. Each droplet is a tiny controlled universe in which the delicate balance of forces is meticulously managed to achieve remarkable precision and efficiency. Researchers and engineers are not only unraveling fundamental scientific principles, but are also applying this knowledge to create breakthroughs in fields as diverse as healthcare, materials science, and environmental technology. When asked how further advances in microfluidic emulsion stability might transform our approach to some of the most significant challenges of our time, the answer is that these advances could revolutionize everything, from personalized medicine to sustainable manufacturing, as the ability to precisely control matter at the microscale opens up entirely new avenues for innovation and problem solving.